If you would like to, you could. I would. It's like really satisfying. So nice. Okay, welcome back, everybody. Hope y'all had a nice break. So we're now going to continue our exposition of quantum codes. We are very lucky to have Nico Breuckmann here from the University of Bristol. Nico is an expert on quantum LDPC codes and also one of the co-organizers of the quantum program. So thank you for pulling double duty and also giving us a talk. And he'll tell us about quantum LDPC codes. This is part 1. Part 2 will be tomorrow. Right. All right. Take it away.
Yeah. Thank you so much for the introduction. Yeah, so actually, I didn't actually know exactly what the definition of a bootcamp was, and I looked it up on Merriam-Webster, and one of the definitions was it's a program where young offenders are forced to participate. And I really hope that I can kind of get some participation out of you, even though it's like quite late. Yeah, I very much encourage you to ask questions and do that. That makes it more fun for me, and I hope it also more taking more out of it. Okay. John's talk has only been 30 minutes ago, but yeah, as you may know, quantum information decoheres very fast. So let me kind of start off with some reminder. Actually, let me give you the title. So it's LDPC codes. And just a reminder of what you've just seen is the following. So in John's talk, he kindly already introduced CSS codes. So CSS standing for Kelderbank, Shaw, and Steen. Quantum codes, and they're defined by 2 check matrices. Called HX and HZ. And the all-important property that they have to fulfill is that HZ times HX transpose has to be 0 mod 2. Everything is done over F2, so I will always kind of skip the mod 2. Okay, that's good. There's an alternative description, and this is using Tanner graphs. So let me draw this. So here we have 3 layers. The middle layer are our bits. Let's say n bits. Then we have 1 layer above, which are our z checks, and 1 layer below, and these are our x checks. Yeah, and we connect a bit with a check if this bit is participating in these checks. Yeah? So for example, this z check acts on these 2 bits. Okay, and then okay, I won't draw any more edges, but importantly, the incidence relation between these nodes and these nodes is encoded in the check matrix HZ, and similarly we have our x checks, and this will be the incidence relation encoded in this matrix. Okay, and now what we've seen in John's talk. Let me find the other big pen. So this important condition, yeah, which is necessary to define a CSS code, essentially tells us that if I pick any 2, any pair of an x check and a z check, then their overlap has to be even. Yeah? So Yes, to kind of look like this. Yeah? Okay, so this is just a more visual way of talking about this, but it's just an equivalent definition. Okay, so now let me give you the definition. The family of CSS codes is pure LDPC, where LDPC stands for low density parity check. If equivalently, HX and HZ are sparse matrices, or equivalently, if the tenor graph is sparse. Yeah? Meaning that the degree of each node is bounded by some constant. Okay, so that's the definition. Let me also say a little bit, so everything has been quite abstract so far, so we talk about kind of doing checks, but I'm sure you appreciate that like a quantum computer is a very physical device, yeah? So the quantum information is held in some quantum mechanical system. So how does it actually work? How can we kind of perform these checks? It's very simple in the classical world. We just kind of, our code word is just a string of zeros and ones, right? You can just look at them and then kind of compute the parity. But in a quantum computer, let's say our qubits are spins, yeah? They're like little spins. And so we have to kind of work a little bit harder to kind of, perform these parity checks. So in particular, so measuring a check involving m qubits involves what a physicist would call facilitating an m-body interaction. Yeah, so sticking with this example, so let's say our qubits are spins or atoms, yeah. Then what an experimentalist would have to do is they have to orchestrate, yeah, kind of getting these atoms kind of close together, make them interact, yeah, and then put them apart and kind of do a measurement, yeah. And you can imagine that kind of facilitating and kind of orchestrating such an interaction is quite involved, yeah. So people have to kind of work very, very, very hard in the lab, yeah, to kind of do this. So I hope I can kind of convey that, in fact, all reasonable codes that we consider are LDPC codes. Yeah, because we can't facilitate arbitrary interactions between our atoms or our spins or whatever system we use for computation. Yeah, so virtually all codes we consider, or families of codes we consider, are quantum LDPC codes. However, this is not a vacuous definition. Yeah, otherwise I would just talk about quantum error correction in this talk, because there's a colloquial meaning to QLDPC. So let me give you the colloquial meaning. Of QLDPC, and this is that these codes have high rate and large distance. And also, usually there's like a notion of giving up physical locality. And I will make this more precise in the next couple of hours. And but one thing I want to kind of say at this point is these two things actually go hand in hand. Yeah? Because it turns out that if we have spatial constraints, then this implies constraints on code parameters. So, for example, there's several results. Let me just kind of highlight one. So we know that if our code in some sense lives in 2 dimensions. So for example, we have just seen the Tory code, which is kind of a 2-dimensional layout, right? And for such codes, we know that the number of encoded qubits times the distance squared is bounded by the number of physical qubits. Yeah? So remember, every code comes with 3 parameters, n, k, and d. Yeah? N is the number of qubits we have, the ones which we encode into. K is the number of logical qubits. This is the degrees of freedom that we encode. And d is the distance. And if you remember from John's talk, for the Tory code, this number was 2, so just a constant. And this was on L by L lattice, this was L. Yeah? And the total number was 2 times L squared. Yeah? So it just satisfies this bound. And it turns out we can't do any better, yeah? If we stay in 2D. Yeah, and this is a bound due to Ravi, Poonam, and Tehan. Okay, so now the reason why we would want to give up physical locality is because of this reason, yeah. Because QLDPC codes kind of promise that we can do better than this, yeah. We can kind of get better code parameters, and there's other reasons to kind of look into QLDPC codes. So one is what Ani Krishna will go into in his talk, where a theorem due to Breuckmann kind of promises that we can perform fault tolerance much more efficiently using QLDPC codes. Yeah, and this is the application in quantum computing. But it turns out that QLDPC codes have found various other applications. So let me just kind of name 2 of them. One is in complexity theory, turns out, because these structures that people have found in the search for good QLDPC codes turned out to be useful for quantum Hamiltonian complexity, also for classical complexity theory, so some of square bounds. And even further removed from this, it turns out that you can use these QLDPC code constructions in geometry. So there are conjectures in geometry which have been proved using the construction of QLDPC codes. Okay. All right. So this was just the introduction and a bit of a reminder. Oh, yes, please.
Three dimension, like can you get better than this equality?
Oh, I will talk about this tomorrow.
Okay.
Yeah. Put a pin in that and then ask me again. Yes. Very good. Any other questions at this point? Yes.
About the n-body interaction.
Yes.
Can't you simulate any n-body, like n-qubit gate with like 2 qubit gates?
There's some asterisks to this, yeah. So there are ways of kind of circumventing this, and I'm not going to actually talk about this. So there's something called subsystem codes where you kind of essentially do this. There's also other kind of ways you can use quantum codes. But if you I'm just kind of talking, if you naively want to implement a quantum code and you want to kind of naively implement these parity checks, then they better not be kind of too complicated. But you're absolutely right. There's like way of kind of circumventing this. Yes. Any other questions? Okay, if not, yeah, then let me talk a bit about constructions of QLDPC codes. Okay, and well, it turns out that I mean, LDPC kind of comes from the classical coding theory, obviously. So we kind of put lazy. We always kind of put like a Q in front of anything that the classical people have come up with. And LDPC codes are just classical codes. So just kind of we ignore one of these 2 codes, yeah, and then we just have a classical code. And LDPC is just defined in the same way. So it just means that the tenor graph is sparse, yeah. And or equivalently, we just have one parity check matrix, and this has to be sparse. In the classical world, we actually kind of somewhat spoiled because it turns out, so for classical LDPC codes, we can just pick parity check matrix H to be random and sparse. and then we are guaranteed that K will be linear in N, and D will be linear in N, yeah, with high probability. Yeah. So we don't have to work very hard to get an asymptotically optimal code. Yeah. So why don't we just do the same thing for quantum LDPC codes? So let's try this. So try this for quantum. In a naive way. So so we just pick, let's say, hx at random. Doesn't matter whether it's x or z. Random and sparse. And now, as a reminder, for CSS, we now have to kind of find the hz, and we require that hx times hz transposed has to be 0. Okay, can anybody kind of already see like where we are running into trouble here? So this equation essentially tells us that the checks of the Z code are code words of the X code. Yeah. But those we know are linear in size, right? So this matrix can never be sparse. Yeah, if we do this naively. Yeah. So maybe we put a star here, and then the star tells us hz cannot be sparse. Yeah. So what do we do now? Yeah. So this kind of leads me into like several constructions of LDPC codes that I'm going to discuss. And
I have a question.
Yes.
Why is sparsity a necessity?
So that was kind of the point I was making here. So when we implement the code, right, we have to perform these checks. Yeah. And I can't go into too many details of how we do this, but it turns out this is like very, very complicated for the experimentalists. So I would love to just tell them, just kind of take a random code, just do it. But then they will come back to me and say like, oh, it's hard, and then I have to kind of do the work. Yeah. So that's how it is.
So some other structure might also help, right? Instead of
yeah, exactly. So we do need to kind of introduce more structure, and in fact, kind of yeah. So I mean, the way to kind of getting good QLDPC codes was essentially first they were like random constructions, and then it turned out that you can actually de-randomize them. But I will kind of get there. Any more questions while I'm cleaning up?
What if you try random but require XD to be sparse?
So it's a bit a question like how would you kind of sample this, right? Because you would have to kind of constrain how you sample HX in the first place, and that's kind of the question, right? Like it's kind of unclear how you kind of set up this ensemble. I mean, it's a good idea, and I think I'm pretty sure lots of people have tried, but turned out that wasn't the way of doing it. Yes, please.
I feel like there is a subtle difference between how a LDPC code is used in the classical sense and this. Typically, in the classical sense, you have your n bits and you have some errors in the n bits. What you get to observe are exactly these erroneous n bits,
Yes,
right?
yes.
But here you get to observe some syndromes of the erroneous bits.
Yeah.
I mean, in classical information theory, I think this is called like the syndrome source coding problem, which is very closely related to the error correction problem, but there are some subtle differences between the two, right? Do any of these play?
Oh, yeah. So I mean, that's kind of plays into the decoding problem that I might kind of touch upon a little bit later, but actually Ani will talk about in more detail. So maybe looking at that. But yeah, it's a very good question. And actually, this is like why we're here, right? Because I think like the decoding problem for QLDPC codes, just kind of say that upfront. I think it's somewhat open, so we don't actually know how to decode them in a good way. So I hope like classical people can really help with this.
I mean, even more than the decoding problem, is this truly an error correction problem, or is this something that's closely related to an error correction problem but slightly a different problem?
I'm not sure how to answer this question. I mean, I would call it error correction. I don't know, maybe
But
somebody else.
well, maybe the classical problem is closer to like code word stabilized codes. So if I think of a general classical error correction code, maybe I'm more likely to think of it as code word stabilized. But for us, quantum side, we almost always work with linear codes,
Yes.
which I think is what this.
Oh, okay. Oh, I see. Okay. Yes. Okay. Yeah. Okay. I still don't know what the answer would be that you're looking for, but maybe we can have chat offline and then talk about it. Okay. So all right. So we kind of talked a little bit about like random constructions and why it's hard. So in fact, turns out that a lot of the initial construction of pure LDPC codes have been done geometrically. And in fact, also including the ones which held the distance-bound record for like almost 20 years. Yeah? But let me start again with our nice Tory code. And I'm happy that John hyped you up. Tory code. And I will have to explain it as a homological code. Or as an example of homological code. And just to remind you again, so we have some square letters on torus. So we have these two sides identified and these two sides identified. And we have our checks. So we have our X checks in blue, which are associated to the vertices, and we have our qubits living on the edges. I'm not going to bother to kind of draw little points for the qubits, just assume that there's a qubit associated to every edge. And then we do our X-parity check measurement here. And then we have our plaquettes, or I will call them faces, here. Yeah. Now, I can kind of rewrite. It turns out the only thing which kind of is important here is like the incidence relationship, right? Like which edge belongs to which vertex and which edge belongs to which face. Yeah? So I can write this abstractly as a partially ordered set, where I put my faces here, and I put a node for each face. And I have my edges here. And I put a node for each edge. And I have my vertices here. But now note that, and they're connected if, let's say, like this face here is this one, right? And it has this kind of connected to 4 edges, which are the ones which kind of go around here. And maybe there's a vertex here, which is this one, and it's connected to, let's say, these two, right, which are the ones which are shared by this face and this vertex, and then maybe 2 other ones. But now you see this set, this incidence relationship between faces, edges, and vertices is exactly the Tanner graph, right? And more importantly, this is also something that John told you, that if you take any vertex and any face, they will always either overlap on 0 edges or they will overlap on 2 edges. Yeah? And it turns out this is a general property of so-called regular Cheng cell complexes. So posets of regular cell complexes contain Tanner graphs of CSS codes. Okay, so I didn't define what a cell complex is. Just imagine I have any topological space, and I just subdivide it into pieces. So I subdivide it into let's say if it's 2-dimensional, I subdivide it into any type of patches, which I then kind of connect via edges, and then I have vertices. So let me give you just an additional example. So additional example. and that's the high-dimensional cousin of the toric code, which is the 3D toric code. Yeah. So I take a 3D lattice or 3D cell complex. Yeah. And imagine I identify this side with this side, and this side with this side, and the front with the back, and I subdivide this into little cubes everywhere. I can also write down this incidence relationship between, let's say, all the cubes, right? Then I have all the square faces. I have my edges. And I have my vertices. Yeah? And each, let's say, each face is incident to 4 edges, right? And each edge is incident to 2 vertices, and so on. Okay. So now, turns out I can just kind of use this and just take, let's say, this subgraph here. Yeah. And I'm guaranteed that this will define a valid CSS code. Yeah. So I can identify my edges again with qubits, and I have my faces as Z checks and my vertices as X checks. Yeah. And this will define a valid code. So what is this code? Let's say we have an L by L by L lattice, yeah? Then I hope you can believe me that the number of edges in here will scale as what? Like how many edges will be there in this L by L by L? Oh, yes, exactly. L cubed. However, and John already kind of told you the logical operator kind of associated here will be a non-contractible loop. Yeah? So how long is this non-contractible loop in this lattice? It's still L. Yeah, exactly. So our distance is just L. Yeah. But this means that our distance is just third root of n, right? So we made a code, but this code is actually worse. Yeah, it's less efficient. So yeah, so this is not the way to go. However, using a much more complicated construction, it was shown in O2 by Friedman, Meyer, and Liu. Yeah, like 5 years after Kitaev, that we can construct a manifold different from the 3D torus and different from the 2D torus, such that the distance is 4th root of log n times square root of n. Yeah. So we beat the toric code by a 4th root of a log. Yeah. And just for fun, let me explain to you how this construction works. So let me just use my hands. So we take a hyperbolic Riemann surface, so a surface with negative curvature, and we look at the translation in the surface. Yeah, and the translation is of length root of a log of the area of the surface. We then kind of trace out this translation and then glue it back together. We get a 3D manifold. And then we take another controlled product in the 4th direction, so we get a 4D manifold. Yeah, and this will have this property. Yeah. So you have to work very, very hard. You don't have to understand this, but I just did it as a bit to kind of show you that you have to work very, very hard to beat the very, very simple trusty toric code. Yeah. Okay. All right. So questions. I'm sure there's questions. Yes, please.
So if you were to implement something like that 4D example, like on, with physical,
right,
2D or 3D, would you get like very non-local interactions?
Yes. So exactly. So maybe let me kind of make a very general comment So these geometric constructions, they don't assume that you have to kind of lay out your qubits in this like 4-dimensional hyperbolic whatever space. It's just to kind of get this graph. Yeah, that's what we want, and we want to kind of then kind of prove these properties. But the nice thing is, geometry is kind of like a tool, because now we can use geometry to kind of prove these things, right? I mean, when we proved the distance of the toric code, we didn't even have to think, right? We just kind of said, oh yeah, it's a longitudinal loop in an L by L lattice. Obviously, it's L, right? And kind of similarly, we can use the very sophisticated tools from differential geometry to kind of prove these things. So it's kind of like just a very nice like bridge to kind of, I know, get a handle on these like very complicated codes. Yeah. But sorry.
Yeah, I had a related question about like that earlier bound. You also wrote about like k times z squared has to be like order n. Like, is that like strictly true for when you have like local checks or?
Yes. So you assume that essentially what you can assume is essentially that this that we can kind of lay out this this graph more or less planar, and then you can kind of prove this bound.
Okay.
And there's other bounds which kind of also hold in higher dimensions and so on. I mean, I should also say this only holds in Euclidean space. This actually kind of breaks if you assume that your underlying space is curved. And then there's other bounds you can prove. But yeah, let me just kind of keep it at that. Yeah. Okay. Yes, please.
So you took faces, edge, vertices to define your Tanner graph. Would you have also gotten something interesting if you had done like cube spaces, edges instead?
I can do that, exactly. Yeah. So I can just kind of shift this up, exactly. The funny thing is about the cubic lattice, it's self-dual. Yeah. So kind of flipping this graph doesn't actually change anything.
That's special to the number of dimensions you're in.
That's special to the number of dimensions and also to the cubic subdivision of the torus. There's other codes where it would make a difference. Yeah, there's other lattices you can kind of tile the torus, and then it does make a difference. But I mean, you never beat this. Yeah, this is kind of like a kind of global geometric property. Yeah, so the subdivision won't really help you. Subdivision really kind of just tells you what the degree of the checks is, not so much like the global properties.
Do we care about the rate as much as the distance?
Yeah, I don't really talk much about the rate here. I will get back to that. So I will talk about rate when we talk about product constructions. The thing is, we can get high rate also with geometric constructions. And I'm kind of tempted to talk about, like, let me not talk about it. Maybe I will talk about it tomorrow as like an extra tweet. But yeah, let me just kind of leave it at that. Okay. Any other questions? Yes, please.
For the hardness of random construction, where did you exactly use the fact that X is random? Did you just use?
I used it because X is random, so I know this.
So it actually holds for any X with a good distance, not only random ones.
Oh yeah, sure. I mean, because of this, right? Because like the checks have to be code words of this, and if this is a good code, this is actually a bad thing. It turns out.
I see. So it's telling you that X cannot be a.
Yeah. That's a weird thing, right? Like it has to be. We want the. There needs to be some kind of like weird gap, right? It's because we want the checks to be sparse, right? So there should be like lots of code words which we use as checks, which are very, very small. But then the actual information is contained in the ones which are very, very large. Yeah, and this is like a weird thing somehow. We have to kind of get a code which has kind of like a weird gap in some sense in its code words. Yeah, that's kind of the difficulty. Yeah. And any more questions? Okay. Let me just kind of draw like one little reminder, and then I'm kind of done with the geometric constructions. So the snapshot is geometric construction particles. So we start with some manifold. Which is subdivided into vertices, edges, and so on. Let me just kind of draw like a musical picture. So it doesn't have to be a two-dimensional surface, but kind of like this. Now we kind of have our qubits uniformly kind of living in this space. Then the number of qubits, n, scales with the volume of this manifold M. And K is just the number of non-contractible loops, or the high-dimensional versions, non-contractible. Just loops in parentheses, because it can be high-dimensional, so it could be these guys, right? And then John already said the distance is more or less loop, or it could be high-dimensional, so it could be a sphere, or even high-dimensional. Okay. All right. Okay, that's all I had to say about geometry constructions so far. How am I doing with time? Okay, I have like 20 minutes. Okay, any questions regarding geometry constructions? That's not kind of.
But this is just for the choice vertices, edges, faces, I guess.
No, so I kind of put loops in parentheses. I will kind of explain tomorrow what I actually mean by this. I mean like non-contractible submanifolds. Yeah. So in 2D, the only submanifold I can have here is just a one-dimensional one. In higher dimensions, I can have something which is, I can have like a surface which is non-contractible. Right. That's why I kind of added sphere here.
Okay.
Yeah. More questions?
When you say proportional, is there a global constant or some? Can it be?
Well, that can depend on like how I subdivide my manifold and like a bunch of other like details. Yeah. Okay. So now I want to talk about the more successful approach in increasing the distance, and these are product constructions. And for this, let me consider the humble repetition code. So what does the tenor graph of a repetition code look like? So I can draw it out exactly. So I have pairwise checks acting on my bits. Then this one kind of goes like this, right? So this is a 313 repetition code, right? Where these are my parity checks, kind of acting on my bits, and the only code words I can have are 000 or 111. Okay. Now let me do my trick in reverse. So earlier I said I can take some cellulation of manifold and kind of turn this into a tenor graph. Let me do this in reverse. So let me just proclaim that these are now vertices. These are edges. Yeah. Then the space I get is this loop, right? Because yeah, these are now my checks, right? Are the vertices, and then I have an edge, which are my bits, and each bit is checked by 2 checks. Okay. And again, code words are just assigning 0, 0, 0 or 1, 1, 1 to all the edges. Okay. Now, the thing I want to convey is, in some sense, a classical code is a one-dimensional object, yeah, because we have these two layers. We have vertices and we have edges, but we have nothing higher, yeah, which we need to define our CSS construction. Yeah. So the thought is, how do I take something which is classical, like one-dimensional, and turn it into something which is higher dimensional, yeah, which is quantum. Yeah. So any suggestion how I take this and kind of turn it into something higher dimensional? Yeah.
Count faces.
Sorry?
Got faces or something like that of the graph?
Yeah. So what I want to do is I want to take. So maybe you've seen that if I take two loops, yeah, and I take the Cartesian product, what do I get? The torus. Exactly. And all right. So what are the and it's not any torus. So if I assume that I have like a simulation here, yeah, I get a simulation here. Yeah. So let me first kind of write down what are my faces. So these will be products between two edges. So one edge here, and one edge here. Yeah, and this will always give me a square face, right? If I take the product of two edges, I get a square face. Now the edges in here are products between an edge and a vertex, or a vertex and an edge. Yeah, and vertices are products between two vertices. Is that kind of intuitively clear? Like this is literally just like topologically what it is. Yeah, and we can define incidences between these and between these. Yeah. And we get yeah, we use this to define our code. So we get our hz and our hx. And what we got was exactly the toric code. Yeah. So this is my magic trick. So I took a repetition code. I took two repetition codes, and I defined the toric code from these two repetition codes. Yeah. So the toric code, in some sense, is like the quantum version of the repetition code. Okay. All right. Any questions? Okay. Also, any unrelated question? Yeah, please.
If you know a decoder for the classical code, you also know a decoder for the resulting code.
That's a very good question. I wish. So I think people are thinking about this, but I think there's also like no fully satisfactory answer, and it's also something we could maybe discuss in the course of this program. That is actually one of the questions I had in mind, because it's not immediately clear. Yeah, how we would kind of implement. You can't just kind of decode each factor individually. You could kind of imagine you can just kind of project down your error, right, in each factor, and then decode on each factor, and then kind of lift back. But this naive approach doesn't really work so well. You kind of lose distance. So you have to do something a little bit more clever. But I don't know. I'm not clever enough, so maybe somebody else has an idea. That's a very good question. Any other questions? Okay. So let me also erase this, and then I'm kind of closer to that side. Okay. Let me kind of rephrase or kind of give it a different symbol to this incidence relationship. So let me call the incidence between faces and edges. Let me call that del 2, and let me call this del 1. Yeah, just a little change of notation, and I always kind of mean this when I kind of talk about incidence matrices. So the question is like, what does the incidence let's say between edges and vertices look like? So that one. Yeah, and I can let's call this del 1 of the product. It turns out that if I kind of write this up, then I get a Kronecker product between the identity matrix times del 1 on the input vector. Let's say let's call this C. Yeah, let's call this E. Then I get the incidence matrix or the parity check matrix of D, and then del 1 C tensor identity. Okay, and yeah, you can easily kind of convince yourself of this just by kind of checking that let's say this edge, yeah, which is a vertical edge, is incident to exactly two vertices, which are the products between like two vertices here. Yeah? So I can fix a vertex here, then I have two vertices here and here. Yeah, and this is exactly the incidence relationship from my initial del C. Yeah, and I don't do anything on the vertices. Yeah? And this is exactly encoded in this matrix. Okay. So we call this horizontal and this vertical. Edges. Okay, and now the last thing I want to talk about is essentially the way the code words in the product structure relate to the code words in the input vectors. Yeah? And this is called the Kunneth theorem. And this essentially tells us that the code words of the factor codes, call them C and D, lift code words in the product CMS code. Okay, so let me just kind of draw it here. This example. So let's say we draw our code word here, which is non-trivial. So let's say 1, 1, 1. Yeah, let me just kind of highlight the edges. Highlight this 1 here. Yeah. Now it turns out that if I take this code word, yeah, then this lifts into a code word in the toric code, yeah, which is exactly this non-contractible loop here. Yeah. And you can see why this happens, because if I just take 0 here and I take 1 here, yeah, and I kind of plug this into my parity check matrix, yeah, then I'm only checked by the initial parity check matrix of the input code. Yeah? And nothing happens on the other side. Okay. Yeah, and similarly on this one. So if I take the code word here on the horizontal edges, then I can lift this into a code word here. Yeah, and these are my two code words that I have in my toric code. And these are exactly like the two non-contractible loops that I have in my toric code. Okay? Any questions? Yes, please.
So you said earlier that you could view the toric code as kind of product of repetition codes. But you could also view the 92-bit shortcode as a kind of, I don't know, like concatenation or some kind of, you know, product of repetition code. So could you say, elaborate a bit more about, like, you know, what's different about it? And then, like, we also heard about CSS constructions, which are also looked up with, I guess, you know, in principle, repetition, classical repetition. So, like, are we talking about the CSS construction here, or are we talking about something different?
No, this is all I'm talking about is CSS, right? Because every time I have two parity check matrices, right? Yeah, which are like my instance relationships between vertices and edges and faces, right? So everything I talk about is CSS. You mentioned
the graph of whatever this product code would be is like exactly the CSS paragraph.
Yeah, exactly, yes. And you mentioned, I mean, I see where you come from. That the shortcode is it's also like in some sense like a repetition version, like quantum repetition code. But there the construction is a little bit different, right? Like there was no as you said, it's like a coordination construction, yeah, rather than like a geometric construction as you like. Okay. Any more questions? Yes, please.
Can you repeat what's the punchline here of this theorem? So you have the code words for C, code words for V. What's the claim about the code word for the third code?
Okay, let me kind of get to the punchline. And the punchline this is work by Tillich and Seymour. Called this. So they had the more the combinatorial view, and they called this construction hypergraph product codes. Okay, so the idea is essentially I took the repetition code here, right? But nothing stops me from taking any other classical code, right? I can take any classical code. I define this product. I get some really strange, like, kind of product structure, but it doesn't matter. Yeah, the whole construction goes through. Yeah, I still get a valid CSS code. Yeah. So what they observed is if I put in, I already said we know how to get classical codes. So know how to construct classical codes with K linear n and D linear n, right? And now I plug this into this construction. Then what do I get? So first of all, I get that my K, so in the product, my K, so first of all my N, so my N will be just N to the squared, right? Because that's the product, right? If I take like a 3x3 repetition code, 3x3 repetition code, I get by a 9x9 torus. Yeah. My K will be K to the squared. Yeah. This is exactly the statement of the Kunnett theorem. Yeah, that I can take any code word of each individual factor. I can lift it, so I get K squared, K to the squared non-contractible loops in this structure. Yeah. But just as for the toric code, because of the Kunnett theorem, or not quite because of the Kunnett theorem, I also know that there's an upper bound on the distance that I can have, right? Because I can take any code word here, kind of lift it into here, but this thing is of size square root, like of square size, yeah. and this is of linear size. Yeah? So the distance can only be square root in the product structure. Yeah, exactly as it is here. Yeah. So the distance at most will be square root of n, and what Tillich and Zehmer proved, it can be exactly n. Yeah. So we get exactly this. Yeah. And yeah, let me kind of stop here because I will kind of go into a little bit of the. Sorry.
Tilde, right?
No, n. Oops, square root. Yeah. Thank you. Yeah. So we can get something which has the same distance as a toric code, but much better encoding rate. Yeah. Because this is again essentially. Okay. And I will maybe tomorrow kind of go into a little bit of like why this is, and again kind of then develop the formalism that kind of makes this kind of set this like homological perspective, but I didn't actually talk about homology, so I'll kind of maybe talk about this a little bit tomorrow. Yeah, but I'm happy to kind of take any questions if you have. Yes, please.
So K theorem, does it also say you can go from the product CSS code to the original classical code? Because without that, you can't argue the distance.
Oh yeah. So it only gives you an upper bound on the distance. Mm-hmm. Yeah, it doesn't give you a lower bound. And lower bounds is like much harder. Yeah. So yeah, but I will kind of get into this tomorrow. Yeah, please.
Yeah, from the product construction, how you would understand the quantum code can be degenerate, or the classical code is always degenerate?
So the degeneracy just comes from this high dimensionality property, right? So this just kind of comes from the fact that you have like these two codes kind of interacting, right? And one being like one set of checks being code words of the other code. That's where the degeneracy comes from. And the degeneracy doesn't exist in the classical case, right? Because you can just kind of pick your parity checks to be linearly independent. Yeah. But you are forced to have linear dependencies once you talk about quantum codes. Yeah. Or these high dimension objects. This way it looks like. Okay. Any more questions? Yes, please.
I mean, I guess you could play a similar game here where you go to higher dimension, but is it similar? Like maybe instead of starting with like 2 loops, I start with like 2 spheres. Or
Yeah. I could also iterate this, right? Like I mean, like the 3D toric code I showed you, I can just take 3 loops and I get exactly that. Yes.
But is it the same sort of phenomenon that you might be starting with 1 dimension always seems to be best for this sort of for the parameters in the end?
Actually, good codes you can kind of think of as starting with two-dimensional spaces, but then two-dimensional spaces with like a really strange way of doing checks. Like they're not. Yeah, let me get into this tomorrow. Yeah. So it's something called homology with twisted coefficients that we do on there. Yes,
I have a really naive question. You are using 9 qubits in the simplest code, 9 qubits to encode 1 qubit. But the probability of errors when you have 9 qubits is higher because of your 9 qubits.
Oh, yeah.
How does it really help?
Oh, yeah. So that's a very good question, actually. So So let me rephrase your question. So the issue is, if we assume, let's say we have some error model, right? Like we just have like independent bit flips on all qubits, yeah. Then like a linear number of qubits will undergo an error, right? But it turns out that even though your distance is lower, you can still show that you can correct back reliability in a reliable way. And I think Annie will kind of talk about this more. This is kind of like called the threshold phenomenon, where, for example, like even for the toric code, right? The toric code only has like square root n distance, right? But the expected number of errors is of order n, right? Because like if you flip each individually, it's like p times n, yeah. But it turns out that if you make your Tori code larger and larger, yeah, there's like some sort of like percolation transition that happens, yeah. And below this percolation transitions, we can arbitrarily like the probability of incorrect decoding goes to 0 exponentially. Yeah, that's a very good question, but I'm not going to kind of talk about this. But yeah, Ani will kind of cover this in his talks. Yes, please.
Is what you said true if distance is any like small power of n, like n to the like 0.1 or whatever? Like would there be a finite error threshold as long as distance is
Oh yeah, even so we can. So this is a result by Priatko and others that actually it suffices to just have logarithmic distance. Yeah,
so as long as distance is scaling like faster than log
yeah.
n,
Yes.
you can have a finite error threshold.
Yes. Yeah. And in fact, there are. I mean, so I didn't. So it kind of goes back to your earlier question. So you can define codes with have logarithmic distance and linear rate, and actually they perform quite well. So these are called hyperbolic codes. So you just kind of take hyperbolic manifolds, you just do their Richier with the definition of the CSS code geometrically, and they actually perform quite well, even though the distance is only logarithmic. Yeah.
What do you mean by they perform very well?
Oh yeah, just kind of if you just kind of look at you just kind of have some toy error model and you just do numerical simulations and then you just kind of compare like straight up compare numerical simulation results with other codes.
In the interest of time, we can take further questions offline. So let's so just a few quick announcements.